Okay? So if I want to measure the voltage on the ground, how do I connect the probe to measure it? Remember that most high-frequency test equipment or high-frequency equipment is not floating. If you have a voltmeter, it's floating. Each one of the two wires is separate, it's not connected to ground. But all equipment which works at high frequency, one side is connected to ground, like in a BNC connector, the outside is grounded. So if I have an oscilloscope, how do I connect it to an outlet to measure the voltage on the ground? So, yes?
Do you want to see the actual waveform or just the RMS value?
No, the waveform.
Could you take a differential measurement to take another probe, connect the ground to the other probe, and then one end in the ground and one end in line socket?
Okay, so let's say I just have this, okay? So one way, because first of all, you have to think about the question, what does the voltage mean? Voltage is always something relative to something else. So this question has no meaning, right? There's no such thing as voltage on the ground. It's voltage compared to what, right? And since usually voltage is reference to ground itself, so this question, when you say measure the voltage on the ground line, is a meaningless question unless you say in reference to which ground. Because if you plug in the scope to the same outlet or next to it, obviously the ground here would be the same as the ground on the other. We measure always zero by definition. But let's say you want to measure, you have two outlets and you want to make sure the grounds are the same. There is no ground loop, what's called ground loop. Okay, so you can plug the scope. This is connected to an oscilloscope, and the oscilloscope has a plug. So let's say you can plug this to the reference outlet. So this clip will have the same ground potential as the ground on the reference outlet. Okay? But, okay, so what do you do now? So you have the outlet, okay, you have the outlet. The outlet looks like this. So, what do I do now? Yes?
You don't plug the ground and you take the tip and plug it into the ground?
Exactly. This doesn't matter anymore, because if I connect this to this, and I create a new ground loop, because if there is really some voltage on the ground here, okay, and I actually connect this to this, I connected a new ground loop, because these grounds are connected internally, okay, and I just create a new ground loop. So what I do is just take the tip and touch it to which one? Which one of the three? The ground. And now, you notice in the outlet, one is smaller than the other. Maybe you didn't notice. Okay? Which one of the neutral and which one is the live one? So guys, you'll be graduating soon. You don't know what's on the plug? so, yes. Pardon? Of course. Okay, then this is the neutral in your house, and this is the live one. Okay? So you better remember that. So because never plug this into this. It will be a big spark. Okay, never touch the ground to this. You can touch the ground to the neutral. It will just get a reference from the neutral instead of the ground. Okay? Now inside the plug there is some three wires connected to these three things. What's the color of the wire connected to the live one? Black. And the neutral? White. And the ground? Green. Green-yellow by code now. Or green-yellow, like green with the yellow stripe. And if this was a DC supply, if this was a DC system, say a battery in a car or anything, so there is a plus and a minus. Which color wire goes to the plus? Pardon? Red. And to the minus? Black. Except in which country? Japan, it's backwards. Very important to know. If you take apart Japanese equipment, it's backwards. But now they're shifting to the standard. Very, very dangerous thing. Like in Japan also, light switches are backwards. You know, down is on. Okay? Very dangerous. Okay. Does somebody know why all switches in the world up is on?
Safety related. when you turn it off, it's like something called.
Yeah, but could be safety related, could be down on too. So there is a special physiological reason why all switches in the world, except Japan again, up is on, down is off. You never thought of that? When you get electrocuted, the muscles contract. So when you get electrocuted, you can only pull things down, not up. Okay, it's very important. Okay, good. So anyway, so now, okay, hope you understand how the plug in your house works now. That's good, but it's very important because you are designing equipment to plug into the system in your house or in an office. So you really have to understand how it's grounded, how it's done. Okay, so again, ground loop is created by the fact, and I'm just reminding you from Tuesday, that in theory this ground should carry no currents. In theory this ground is only for safety, so if the metal case of the body touches the live one, it will blow the breaker, because the ground is like the neutral. So if and this is connected to the case of the equipment, so if this some wire chafes the insulation and touches it, it will blow the breaker. But in reality there is leakage currents, so I want to remind you again that in reality, if this is again your outlet, so this is a normal load, so this is a load, and the idea was that if this touches this, it will blow the breaker, but in reality there is a leakage current because of imperfect insulation and so on, and because of this leakage current, which could be quite big, because it will not going to blow the breaker, right? So because of this leakage current, there is actually currents flowing in a house over the ground wires. Okay? So two grounds in two rooms are not really the same potential. And this creates ground loops, and our concern with ground loops, if we have a system and it has a sensor in one room and a controller in another room, the reference is not the same. Okay, so in some systems it's a big problem, like in audio systems. So the typical solution to that, as you recall, if you are very sensitive to this, that your reference is not the same reference, if you are very sensitive to this, you have to bring all the grounds to one point and then ground it. So, because if you have a ground wire as part of the outlets, and there is a current flowing here, there will be a delta V. So two pieces of equipment will not have the same ground. But if you have multiple pieces of equipment and you bring all their grounds together to one point, and then this point is connected to ground, then there is no delta V because there is no current flowing in this part of the wire. Is that clear? Is it completely clear? Or? Okay, good. But again, a reminder, if this was RF, you cannot do that, because if there's a high frequency system, if you have very long ground wires, you can have a potential at one end and no potential at the other end because of a different problem, because if this becomes a significant part of a wavelength, you can have just because you can have in a wavelength at the two ends, you can have zero voltage, in the middle you can have maximum. Remember? So once it becomes high frequencies, you can't do that. You have to connect everything to the ground at the nearest position to minimize the length of the ground wires. And also in high frequencies, the ground wires also have inductance. Every wire has an inductance, as we discussed before. So if you're dealing with high frequencies, the impedance of the ground wires becomes very big because of the inductance, so it's no longer a good ground. Like if this is a microhenry, okay, but if you have you're working with 100 megahertz, then the ground, even a meter of wire, is a very bad ground because of j omega L. It actually looks like a big impedance. So for low frequencies, distributed systems, you sometimes may have to do this, and that's called central point grounding or audio style grounding. For high frequency, you don't have the choice. High frequency, you have to do this, while in low frequency, you have a choice. You can do this or this, depending on the circumstances, what's most appropriate. Okay, so the same thing applies when you want to measure very low level signals. So the equipment you're measuring and the scope should be plugged into the same outlet. Because if the scope is plugged in some power bar which is connected to an outlet and you're measuring some equipment, automatically there's going to be a difference between your ground reference in the equipment and the ground of the scope. Okay, so you're going to pick up not just the signal but also some differences between grounds. Clear? Good. Okay, I just want to pass along two things before we start the lecture today. One is a very historic piece. This is a piece from the actual first transatlantic cable of 1858. And this is a cable which started all the studies and understanding of transmission and all the things we talked about, how to connect things with long lines. Coax, waveguide, matched impedance, all these concepts of signal transmission. It all started because the first cable didn't work. Okay, that gave the impetus to people to understand what really happened. So this is a piece of the actual cable. Now, this was before polymers were invented, so the insulation of this cable, it's not plastic, because plastic didn't exist. Even vulcanized rubber didn't exist. So the insulation of these cables was made from sap from the rubber tree, what's called caoutchouc, and it was dried and thickened, but it wasn't really vulcanized. Vulcanized is the rubber like the way you know it today, where you take the sap, mix it with sulfur, and make it into rubber. And who invented this? Goodyear, of course. That's why Goodyear Rubber Company is called Goodyear. But before Goodyear, people didn't have even rubber, so you could only insulate with if you wanted rigid insulation, there were some choices like molten sulfur and so on, like sulfur. But if you wanted a flexible thing, there was no material available which is flexible and an insulator in the whole world. So that's why it's so difficult to make a cable. But the real reason it didn't work is mainly because of understanding of this impedance and transmission lines and so on. So anyway, so pass it along. Okay, and I want to pass along another piece. I want you to see, for those who haven't seen, what does an enclosure look like when you're dealing with high frequency. So I mentioned at the end of Tuesday that at very high frequencies, even a small distance can be a fraction of the wavelengths. So even if you have a hole or a slot, it can act as an antenna to transmit or receive noise. So when you do shielding at very high frequencies, and sometimes you have to protect yourself from high frequencies, although your unit works at low frequency, but the noise can be very high frequency. So even if you don't want high frequency, you have to protect yourself from them. So in sensitive equipment, the shielding has to be very thorough. So I mentioned a few things that, first of all, if you have covers, you have to put many screws in order to make sure there's no gaps in the shielding. So I just pass it along so you can see how many little screws there are, about 20 of them, just to hold a little cover. And also, the shielding on the coaxial cables is made of solid copper. It's not a braid. Because even a braid, when you have a mesh, there is teeny holes. It's not perfect copper. It's not as good as solid copper. So above a certain frequency, all the boxes have no ventilation holes. If you want to cool it, you have to put fins on the outside. But there's no ventilation holes. And all the cables at some point become solid, or at least multi-layer shield. But the best is solid. So this box is a 15 gigahertz amplifier, oscillator amplifier. So this is all solid, with solid copper. It looks like plumbing. Okay? If it was 1 gigahertz, you can get away with a very dense shield and maybe a few less screws. If it was 1 megahertz, you could get away with just a coaxial cable, any coaxial cable, even 10 megahertz with slots for ventilation. And if it was a few kilohertz, you can do whatever you want. You can run a twisted pair, you can have cover, no cover, nothing matters. But I want you to see what something looks like if it has to go at the very, very high end of the frequency. So just have a look at it, pass it around. Okay. So now we move on to today's subject, which is filtering. So why do you need filtering at all? Because, you know, if you are inexperienced, you think about it. If I have a servo loop, let's say if I have a controller and I have a sensor, I have an actuator, I have a servo loop, okay, and I have an input. So let's say the actuator is not capable of high frequency. Let's say that's a stepper motor. And the sensor could be any one of the sensors we discussed, okay? So inexperienced people look at it and say, I don't really care about high frequencies because a stepper cannot respond to them. In other words, the actuator typically has limited bandwidth. If this is a solenoid or a stepper, it really can't respond to megahertz signals. So why do I care? Why do I need filtering? This wouldn't respond anyway, so I don't care. But that's a big mistake. It turns out that in any servo system, I could expand it and say, in any electrical system in the world, you have to have filtering. Because inexperienced people don't understand that and also miscalculate the value and position of the filtering. So I want to list a few reasons why do you need filtering, and usually you need more than one filter. So typically you would have to insert here, okay, you have to insert here a filter, and sometimes you will also have to insert here a filter, but this is less important. Up. And sometimes there are even more filters. But the one filter you have to have in any servo system is a filter in front of the controller or in front of the amplifier. And if the controller, meaning if it's a complex servo with digital, if it's a simple servo, this could just be an amplifier, like in an analog servo. Okay, so why do I absolutely have to have a filter? So it turns out there's many reasons for that, and we start listing them and explaining them. So can people suggest why is it so important to have a filter? Yes?
You can band limit your signal.
You can band limit, and why is it so important to band limit? Because why can't I say the actuator can't respond anyway? Why do I need to band limit? The system itself has a bandwidth limit. So it turns out there are at least 4 critical reasons why you have to have a filter. Close. Okay. So keep thinking in that direction. You band limit. Why do you have to band limit? Okay, so anyway, I'll start listing them. The first and most common reason in modern systems is aliasing. Because, I'll explain first, maybe some of you don't know what it means. In most modern systems, this is actually processed digitally, which means somewhere here there is an analog to digital converter, and the way it typically works, when you have a waveform, let's take a simple sine wave, the analog to digital converter samples it. Sometimes there's even a module inside called sample and hold. So when you buy a block like this, which is called ADC, analog to digital converter, inside there is typically something called a sample and hold, which samples. And then inside there is a converter. There's the actual converter which comes out with binary or BCD or whatever. Okay, so that's another, and this is input. And there is a clock here which clocks at the rate it samples. Okay, so we already know that if I want to capture the signal, there is some theoretical limits. How many samples do I need to sample for a signal of frequency f? 2f. Okay, and who came up with that rule? Oh, good. Okay. So, and of course it's a theoretical limit, but if you sample at a signal at 2f, it doesn't work. It's easy to see, because you know the example given always you sample here and here and here and here, so you get a square wave because the sample is held till the next sample, and the sample is held till the next sample, so you get a square wave. But the square wave, when you filter the harmonics, you get back the sine wave. Okay, but it doesn't work because you can also sample by mistake here and here and here and here, which is also 2f, and you get 0 all the time. Okay, so 2f is the limit, but that's only true if you can control where you sample. So it always has to be a bit faster than 2f. Okay, and there is something here which people don't quite intuitively understand. that when people look at a sine wave, let's say you have a sine wave like this, and you know already it has to be a little bit faster than 2f, because otherwise you can hit all the zeros. So you say, okay, I'll sample here, and here, and here, and here, and here, and here, which is like 2.5f, okay? So when I draw the waveform that I get, this is held till this sample, this is held till this sample, this is held till this sample. So when I draw the waveform I get some very strange waveform like this, which doesn't repeat itself. It only repeats itself after many cycles, because you get a beat, right? If you sample, so you get something like this, and maybe like this, and like this, and like this, and like this. So when you look at it, you say, how do I get back my sine wave from Z? Because a few of the samples can hit near 0, and then suddenly it becomes very small, and then it becomes big again. So when you look at this thing, you say, how do I get back my sine waves from this? Even if I smooth it, I get some sine wave, but it seems that the amplitude will be fluctuating all the time. Okay? So the explanation, of course, that Nyquist rule only holds if you have a perfect recovery filter. So there is another part of Nyquist rule which is never mentioned, that you can have to, it's enough to sample a 2f and recover the signal if you have a perfect recovery filter. Because what you are getting here, you are getting what we call an AM signal. If you draw it for a long time, you will get the sine wave, but because of sampling which hits at random places, you'll get a sine wave which looks like this. At some point it's smaller, at some place it's bigger. Like here, when you happen to hit a bunch of samples near 0, the sine wave will look a bit smaller. Okay? But I already mentioned before that this is just a fundamental sine wave plus a few components. Because you can represent this signal, if it was a pure sine wave, spectrally, it will look like this. But if it's a sine wave like this, whose amplitude seems to be unstable because of sampling too close to 2f, it actually looks like it has sidebands. Okay, like it's AM modulated, but so it has, let's call it harmonics to make it, let's make it simpler. Let's say it has harmonics, and to make it simpler, we say if things have harmonic and you have a perfect recovery filter, which can separate the sine wave from the harmonics. Okay, all the harmonics will disappear, and then you're going to get back a pure sine wave, because if there are no harmonics, all that's left is a pure sine wave. So the other unspoken part of Nyquist is you only get back your signal if you also have a perfect recovery filter, which is also hard to realize. Okay, so this is sampling theory. Now what happens if you start sampling if your signal becomes too fast? Let's say the signal at points becomes too fast for the sampling rate. What happens? So you keep sampling at this rate, but clearly the signal is too fast for it, much beyond Nyquist. So what happens? If you connect the points, you get a frequency which didn't exist in the original. Right? So I'll just draw it here so it's clear again. I have a piece of the signal which is way too fast. And I sample fast enough for the original signal, but certainly not fast enough for the new signal. So because the new signal is much faster, when I connect the points here, I'll get some artificial signal which didn't really exist after connecting the point. And that signal would have a frequency which actually didn't exist. So this is called aliasing. This means I create fake signals which didn't really exist. Okay, so the first reason I need a filter is that in any system which has an A to D converter, if I don't have a filter which limits the bandwidth to well below half the sampling frequency, I'm getting aliasing. Theoretically, you have to limit it to half the sampling frequency, but because of all these practical problems, I would say in a practical design, you have to limit it to maybe a third of the sampling frequency, not to half. And it's much better to limit it to a tenth of the sampling frequency. But sometimes you really need all the bandwidth you can get. So about the best you can do is sample 3 times the signal. 10 times is better, 3 times, but if you really sample at 2.1 or 2, it will be very hard to recover the signal. Okay. Okay, so we covered the first reason. Now, let's talk about more reasons. Okay, so one reason which is clear to everybody is there is noise. We talked always about noise which is being picked up everywhere, and you don't want this noise to go through the system even if the actuator cannot respond to it. So, can somebody think of a couple of reasons why you don't want the noise to go through the system even if the system cannot respond? Yes? No, just keep thinking.
Could it like have constructive interference with the wave?
Very close. Okay, so first of all, if the noise is amplified, it can close its own loop through parasitic feedback. We talked a lot about what's called crosstalk and parasitic feedback. Let's say there is a bit of stray capacitance between here and here. At the frequencies we are working, this stray capacitance is not a problem. Because if there was some stray capacitance here, or coupled inductance, in other words, if there was any parasitic coupling, okay, in our frequency it's not a problem because typically this is very low values. But if there is no filter, noise can go through the system, and the noise can be high frequency, and for the noise, this parasitic capacitance shows up as a much lower impedance. Okay? So say if this was a thousand puff, like a picofarad, and we dealt with audio frequencies, we never would know there is such a parasitic capacitance. But if a noise at 100 megahertz will come in, this pass will look to him like a very low impedance pass. So then the whole system will start oscillating. And there's another reason. If you remember the stability criteria, you need a gain of 1 and a phase shift of 180 degrees in a negative system to oscillate. And we've spent a lot of time on that already. But at high frequency, there is much more chance there will be a phase shift of 180 degrees. Because the source of phase shift is delay. So the delay is constant. Every system has a delay, delta. So let's say this delay is a microsecond. So at our frequency, this delay doesn't really cause much phase shift. But if a 2 megahertz signal can get in, or a 1 megahertz signal, 1 microsecond is 360 degrees. So even a half a megahertz signal gets in, if this is a microsecond, it's a full phase reversal. Okay? So if we don't limit high frequencies, we can get oscillations in the system, not at the frequency we are trying to control, but the high frequency, which finds it much easier to shift the phase and to feed back. Okay. So the second reason is parasitic oscillations. So basically let's do it like this. The second reason is noise, but noise has a couple of problems associated with it. Okay, the first problem is oscillations. Because the noise is of a higher frequency and more likely to oscillate. Okay? Now the second problem that noise causes is actually very surprising, and probably you're not aware of it. Every system has some nonlinearities. So when a high frequency gets together with another frequency, which is our frequency of interest, in a nonlinear system, it creates new frequencies which didn't exist there. And these new frequencies can actually be in the range that the actuator can respond to. So let's go over that, because I think this is a concept that you're not aware of. That concept is called intermodulation. And without going too much into the math of it, I'll just give one mathematical example so you can see how it works. Okay? Let's say if you have a linear system and you have a sine sine omega t, which is the signal we're interested in. And then another high frequency enters it. Okay, sine omega t, and then we have sine, let's say, omega 1 t, and this is our noise. Let's call it, okay, this is our noise. And any operation you do, if you take this and amplify it, so it's multiplying by a k, anything you do linearly, you still only end up with these two frequencies. They are bigger if you amplify them, but you don't generate new frequencies. But if you have anything nonlinear here, you will get out, if you put in omega and omega 1, you will get out here, not just omega and omega 1, but you'll get out here omega plus omega 1, omega minus omega 1, 2 omega minus omega 1, 2 omega 1 minus omega. You'll get out a whole bunch of frequencies which didn't exist. And some of these frequencies will be in the range the actuator can respond. Okay, so let's go to just in a simplified case. Let's go through the math so you can see it, because it's something which is actually one of the few things it's easier to see through the math than to see through the intuition. Okay? So now, so when we say something is nonlinear, we mean that, remember the definition, that f of a plus b is not f of a plus f of b. Okay? Because this is, if it was equal, that was the definition of linear. Okay, so let's take a square law operation. If you take a plus b and we put it into a nonlinearity which is square form. Any nonlinearity can be broken down into a polynomial representation, because when you have a graph, a nonlinear graph, you can represent it by some polynomial. So let's take the simplest case just to, so let's say the nonlinearity is a square type. So that if we have in and out, instead of getting a straight line, it starts saturating. Okay, that's very common in amplifiers. Start saturating, so this will be actually an inverse square, but it doesn't matter. It's nonlinear. So if we have a plus b and the function is square, obviously a plus b squared is not the same as a squared plus b squared, because you get a new term to ab. So if we have a sine and a cosine, we feed them into a system where the nonlinearity is square, so we get sine omega t plus sine omega 1t squared, so we get sine omega t squared plus sine omega 1t squared plus 2 sine omega t sine omega 1t, and we immediately recognize this because sine x sine y is actually the sum or the difference between two sines, right? Because you know that if you take you know the formulas which if you have sine a plus sine b, okay, it's 2 sine a minus b over 2 to cosine a plus b over 2. So you recognize right away that this is actually the sum of two sine waves at frequencies omega plus omega 1 over 2 and then omega minus omega 1 over 2. Now, I don't even bother to differentiate between sine and cosine right now, because sine and cosine is the same frequency, it's just shifted 90 degrees. So I'm not even going to bother to write down the cosine terms, because all that I want to point out is that new frequencies are created. Okay, so if you have terms like this, which are a product, it actually means it's a sum of something which is omega 1 plus omega 2 over 2, and also omega plus omega 1 and omega minus omega 1 over 2. Now let me just check if that's correct. No, without the 2. Without the 2. Because if you had sine of this plus minus sine of this, what you will get is a product where this will be this plus this divided by 2, and this will be this minus this divided by 2. So if I take this plus this, omega 1 cancels out, I get omega. If I take this minus this, okay, then this will cancel out, I get omega 1. So basically what happens, the moment you have, because of the nonlinearity, you get a square or a product. This is the same as sum of two signs at new frequencies which didn't exist in the original. Now you can imagine if this was a cube. A more common nonlinearity is cubic. So if you have sine omega plus sine omega 1 t, and if the nonlinearity was cube, now you'll get, first of all, the cube. You get the sine omega cube plus sine omega 1. It's all t times t cube. But then you'll get a whole bunch of products here. You'll get a whole bunch of products which look 3a squared b plus 3b squared a, right? So you get a whole bunch of products here which are 3 sine omega t squared times sine omega 1t, and then you get plus 3 sine omega t times sine omega 1t squared, and so on. Okay? So now each one of these can be again broken down into sine times sine times sine omega 1, and two of them give you a sum, and you multiply the sum by the third one, and you start getting more and more components. So when you do this analysis to the end, you realize that from two simple frequencies here, you ended up with two more frequencies, sum and difference. And if it's a cube, if the nonlinearity is a cube, you'll end up coming out with omega and omega 1, which were your input. And you'll find out, you also come out with 2 omega minus omega 1, 2 omega 1 minus omega. You'll also come out with omega minus omega 1, and omega 1 minus plus omega. So you end up with a whole bunch of frequencies which didn't exist. So some of these frequencies will actually be able to go through the actuator. So let's take a numeric example. If this is a 1 kilohertz system and the noise is, let's say, 2.5 kilohertz. So you say 2.5 kilohertz is no problem, it can't run the actuator. But if you can have this type of components, okay, you can have 2 kilohertz minus 2.5, which is minus half a kilohertz, which is the same as half a kilohertz. It's the opposite phase. And you can have any combination which will fall into the passband. Okay, so I went very quickly through it because it's beyond the scope actually of this course, but is the concept clear that any nonlinearity will generate sum and difference frequencies of the form m omega 1 plus minus n omega 2? So when you enter a system with omega 1 plus omega 2, if there is any nonlinearity, you end up with a whole bunch of frequencies which some of them could drive the actuator. Okay, and this is called intermodulation, and that's very bad. It's especially bad in telecom systems because these frequencies which didn't exist can actually jam other channels. Right? If you have a system which operates with many channels, it's even worse. Okay, so noise can do oscillations, noise can do intermodulation, or called for sure intermods, and noise can do something surprisingly different. There's two other bad things noise can do. One is actually surprising. Sometimes the noise is much larger than the signal. Okay, because when we assume signal and noise, we intuitively think the signal is big, the noise is small, but that's not true. When you have sensitive sensors, the noise is much bigger than the signal. Like for example, inside the receiver of a cell phone, the noise, which is all other stations, is like 100 times bigger than the signal, because you are receiving just one station and everything else is noise. So in most cases, actually, in sensitive detectors, if you don't have a filter, the noise is much bigger than the signal. Now, since the amplifier is designed for the signal, and the noise is much bigger than the signal, it will saturate the amplifier. So you say, if you took a cell phone and you put an amplifier without filtering, it will saturate, it will jam, because it picks up all the TV stations, radio stations, other cell phone towers. So obviously the sum of all the noises is much bigger than the signal, so it will saturate the amplifier and you'll get no signal. Okay? So another thing which could happen is saturation, or stealing power at least. Saturation. Okay, and there is something which is very unexpected in the sense people don't think of it, that if the noise goes through here, it comes out here much stronger because it goes to an amplifier, so it gets retransmitted as a bigger noise to interfere with other things. Right? If you think of it, if you have a big amplifier, let's say you have a servo system, this is a milliamp. A sensor drives it with 1 milliamp, but the actuator needs many amps. So any noise which is picked up at a milliamp is retransmitted here into the air as amps, as like 1,000 times stronger, right? So basically you are just making a noise generator because you have an amplifier without a filter. Okay? So this is retransmission. Okay, so you can see that simple noise getting into a system has many, many bad effects. So you can't have a system without a filter. You already know the filter has to be of the bandwidth compatible with Nyquist rate. So again, when you think of all that and you give it to an inexperienced engineer, they tend to put in the wrong filter. And let me explain what I mean by the wrong filter. Okay, so let's say that we know already that this is frequency, this is amplitude. We already know that our sampling frequency is here. We'll call it F sampling. Okay, so we already know that theoretically we should limit our signal to here. So this is F sampling over 2. We know that theoretically the filter should not allow anything above this to pass. Now we already know that practically, because of this reconstruction, we really should limit it to a lower number. So this part is it. But now we have many choices of filters. We could pick a filter which looks like this, and let's call it shape A. Now we can pick a filter which looks like this, and let's call it shape B, and we can pick a filter, say, which looks like much more gentle filter, and let's call it shape C. Okay, and we already know that the cutoff, or 3 dB point, should be much below F sampling over 2. Now, which one of the 3 filters would be best for a servo system? So I drew 3 curves, A, B, and C. Which one would work best for a servo system? Yes?
Protestant.
Pardon?
The plot A.
A. Okay, and why is that?
Because you get linear response for
all frequencies come through the same. Okay? How many other people think, how many people think it's A? A. How many people think it's B? Same number. How many people think it's C? Okay, so the surprising answer that the filter which is best for a servo system is C. And A wouldn't work at all. Okay, if you put a filter A into a servo system, the system wouldn't work at all. And the reason for that is that we drew right now the amplitude response, but we didn't draw 2 other things which go with it, which are linked, the phase response and the impulse response. Because the steeper a filter is, the more phase shift it has. Now, if you remember your basics, when you take an RC circuit, and you draw a border plot, okay, this is a border plot, this is a 3 dB point, okay? So sometimes on the same border plot, you also draw the phase response. And the phase response looks like this, if you recall. It comes up here. So what I'm drawing here is phase. Okay, this is amplitude, this is phase. And it reaches 90 degrees. For a simple RC circuit, the phase reaches 90 degrees. The phase here at the 3 dB point is 45 degrees. Okay? But if I had a filter which is steeper, let's say I did some tricks here. So I added some inductors to make the resonance, to make the filter steeper. I would get a steeper filter Okay, but I will also get a bigger phase shift, because if I have what's called a second order network, the phase shift is now not 90, but now the phase shift will go to 180. So the steeper I make it, the higher order network I'm going to, and as you recall, for each pole pair, I don't know if you are familiar with network theory, but basically, to make it simple, for each 6 dB per octave slope, you add 90-degree phase shift. Okay? So the steeper you make the filter, the bigger the phase shift. And we recall from servo systems that phase shift is very bad, because the phase shift starts much before the cutoff of the filter. If we call this the cutoff, 3 dB point, the phase starts shifting much before that. Okay? So the first problem is that filters which are perfect in the frequency domain have big phase shifts, and they can destabilize the servo. And there is something which is related to it, and I wouldn't go through the math, and what is related to it is the steeper a filter is in the frequency domain, the more smeared it is in the time domain. So when I take a pulse and send it through the simplest filter, the simplest filter is an RC filter. So when I send a pulse through it, this was the input pulse, what I'll get coming out is this. Okay? Now what happens if I take a steeper filter and I send a pulse through it? So the best way to, again, I don't want to go through the math, but intuitively, imagine a filter which is very, very narrow, like this, and very sharp in the frequency domain. So this is amplitude, this is frequency, and you have a very narrow, very sharp filter. Okay? So if I send a pulse through it, this filter, because it's very, very sharp, cannot represent the pulse, because this filter can only pass one frequency. What does this mean, actually? This means like something which, no matter what you put in, can only output one frequency, f. So when I put a pulse, the same pulse, through this filter, what I'll get is something like this coming out. So this was the original pulse, and from this original pulse, all will come out is just a sine wave which grows and dies. So this doesn't even look like this. Okay? And of course, this will also have huge phase shifts, but if I forget even the phase shifts for a moment, if I just think of the time domain, if this was like a shaft encoder, and the shaft encoder was running at fairly constant frequency, so I can say, let's put a very sharp filter to cut all the noise out, but a very sharp filter means it can only output a one frequency if it's a band pass. Okay, and if it's a very sharp low pass, okay, it's also the same. It can only output basically a very sharp frequency near zero. So what it means that any filter which has very sharp cutoff in the frequency domain has to have ringing. That's called ringing in the time domain. Okay? Now, of course, you can prove all this mathematically, because you take because one is a Fourier transform of the other, right? So if you have in the time domain an impulse, you get sine x over x, which goes on forever in the frequency domain, and vice versa. Okay? But without going into any math, you can see intuitively if a filter is very sharp, it can only output one frequency. Now, if it could do that, it couldn't be sharp, because this implies a Fourier transform of many components. To reproduce a pulse like this in the frequency domain means something which has many, many frequencies. But if the filter is so sharp, it can only pass one of those frequencies. It cannot look like this. It has to look like this. Okay, I just made it very, very simple, very intuitive, but you should have taken some course somewhere about this so you understand it. Good. So, surprisingly, the filter A, which looks the best, cannot be used in servo systems. A, because it will have huge phase shifts. B, in the time domain, if you're sending any pulses, it will totally smear and distort the information. And there are some filters which are optimized as a trade-off. Okay, because what you really want is a filter which doesn't have much phase shift and doesn't distort the shape of the pulse. You want it to filter. So what you want ideally, if this is some pulse, okay, say, or maybe you can have a faster pulse, and there is some noise riding on it. Okay, you want a filter which removes the noise but doesn't really distort the shape of the pulse, doesn't add phase shift. And turns out that those filters are very, very rounded, and there are two types which are particularly popular. One is called a raised cosine, because it's the same as a cosine function, just raised above 0. So most telecom equipment uses this raised cosine filter, like modems and so on, because they don't want to distort. Now another filter which is popular is a filter which is called a Gaussian filter, where the shape of the filter is just like E minus x squared. Now Gaussian filter is very interesting because the time response and the frequency response are identical. So Gaussian filter, it may be the only filter that when you send in a square pulse, it comes out Gaussian. So this was the input pulse. Comes out Gaussian, and if you plot the frequency response, it's also Gaussian. Okay? It's not a sharp filter. Obviously, they're all not sharp filters, but they're ideal in terms of phase shift and pulse response. And then there is a few other common filters, Chebyshev and Butterworth. Are you familiar with what the Butterworth filter is, Chebyshev filter is? Okay. So basically, like the four most common filters historically were those. Today you can tailor using a digital filter implemented in software or hardware. You can actually tailor the ideal filter, because you have much more flexibility today in tailoring the shape of filter you want. Okay? Because the classic filters were basically either this, or this. But with digital filtering, you can tailor the filter. But the most important thing to remember that the filter which looks nicest on the time domain, like the steepest, is actually the one you can't use. Now, so what about this? What about the fact that these filters, which are good for time domain and phase shift, actually don't cut out all the high frequencies? So we must have some rule or definition how much is allowed to be left of high frequency after half the sampling rate. I'm talking about this tail. Because anything above half the sampling rate will cause aliasing, and even anything in this area will be bad. So there must be some rule how much of this can be left. So what makes sense? What is the intuitive rule? So if you have to think of it, so I think we agreed that if this is f sampling over 2, we agreed a good filter would be something like this, but because we don't want a sharp filter, it will have a tail left which may even pass into f sampling over 2. So my question is, how big is this tail allowed to be? Because if we say this tail is 0, if you say we are not allowed this tail, it means the filter has to be shifted like this and we lose information. Right? So there must be a trade-off. Obviously you can make a narrower filter, but then you lose information. So there must be some trade-offs that you get the most information you can, and you have some tail extending beyond fs over 2, but it's not harmful. So what do you think would be that size? It's a very simple thing. Think of if you had to design it, what would be allowed? Well, obviously if that's less than a bit, you don't care, because the whole system it's quantized. So if it's an 8-bit system, it's quantized if it's smaller than the last bit, the system doesn't see it. Okay? So for an n-bit system, this thing has to be smaller than 1 over 2 to the power of n of the signal. So it has to be less than that, because if it's less than that, the system doesn't see it. Okay, and that's what allows you to gain some bandwidth, because you are allowed a very small tail. Okay? But in reality, you're losing some information, because if your signal spectrum was like this, and you put this filter, obviously you're losing some information, but you don't have any choice. If you didn't do that, then you'll have other problems. Phase shifts, okay, ringing. So it's always a trade-off. So short answer is you put in a filter where the cutoff is smaller than f sampling over 3 instead of the theory, which is f3 over 2, and you put in a smooth rounded filter, not a steep filter, and whatever is left has to be less than the least significant bit. Good? Okay. Now, another consideration, sometimes in spite of all this, in spite of putting a filter here, it's also a good idea to put a filter here, especially in modern systems like digital servo. It's also a good idea to put a filter here, and actually they all do. All digital servos have an output filter too. Can somebody think why? Why in old systems it wasn't important and in new systems it is? Think of how a PC power supply works, or how a servo amp works today. So, what's different between a new servo amp or a new PC power supply than one 50 years ago? Switching, because everything today is switching. And switching means what comes out here, when you put in a sine wave here, when you put a scope here and look what comes out, you expect to see a big sine wave coming out, but what you see instead is a whole bunch of pulses which switch at a very high frequency, and the average of these pulses is a sine wave, but you don't see a sine wave. Okay? You just see very fast pulses at frequencies as high as a megahertz in a PC power supply and as high as 20 kilohertz, say, in a motor drive or a servo amp. Okay? So you actually see a lot of high frequency and high current. This is very bad. Okay, so you have to limit it. You have to filter it so it doesn't radiate and get picked up by the input and cause all kinds of problems. So some of this filtering is already built into the amplifier. So when you take apart a PC power supply, you have all the switching section, and after the switching section, you typically have this. A typical filter is made by a coil and 2 capacitors. So any servo amp you take apart has this on the output wires. But even this is not perfect. Sometimes if you have a sensitive system, you have to run it through many filters. In some equipment, you can even see they have a filter on the power line coming in. Okay? Another example is when you look at your computer cables at home. If this is your computer cable and it plugs in here to your computer, you see some hump here, just like on a camel, on many cables. Do you know what's inside that hump? What? Ferrite, yeah. If you ever opened it inside, there is just a ring of ferrite. Ferrite is a magnetic material which works at high frequency. So, of course, the ring is split into 2, so you can assemble it on the cable. Okay, and this is a filter, because what it does, it increases the inductance, so it puts more inductance here, so it's a low-pass filter. Okay, so this is the same as this, because there's capacitance in the cable and it adds inductance. So basically, because everything is switching today, you need filtering everywhere. You need a filter on the input against noise. You need a filter on the output here, because this is switching. And sometimes you need intermediate filters in different places inside. Okay? Now this filter, like this is just against high frequency noise, so you don't have to worry about the exact frequency. Like when they put a ferrite on a cable, it's not calculated to an exact frequency. So this is just high frequency filters. The filter which is critical is the input filter, because this has to be matched. If it's a digital system, it has to be exactly trading off aliasing with all these other things. So it has to be critically specified. Good. Like, in theory, this need for filtering exists everywhere, not just in electrical engineering. In theory, if you make an optical system, you also have to put some color filter, not to pick up stray light. If you make a hydraulic filter, hydraulic system, people put in a filter in the form of a restrictor. Okay, but the reason why it's more common and much more developed in electrical systems is because it's much easier to implement. Like if you have a mechanical system which resonates or oscillates, it's very difficult to put a filter. People sometimes put damping. But if you think of it, a mechanical system, it's not so easy to add filtering and tune the filters. But in the electrical system, it's very, very easy, both in analog and digital. So the reason why there's a lot more attention given to filtering in electrical systems, although all systems in the world need them, is it's very difficult to implement filters anywhere except in electrical systems. And that's one reason it's much easier to design an electronic servo than a hydraulic servo. Because when you need some filtering in a hydraulic servo, it needs a lot of thinking how to provide that filtering. And then sometimes you can't even help it. Like, you know, in houses, sometimes there is what's called a water ram. You hear the pipes making big noises. In an electrical system, you just put in a filter, and then it wouldn't oscillate. But in the piping system, you don't know how to do it. It's not so simple, right? So there's a lot of examples that problems which are trivial to solve in an electrical systems are very difficult to handle in other systems because you don't have the tools. You don't have the design tools, and you don't have the tools to actually build a filter of an arbitrary curve. Right? In electrical system, and including optical. By the way, in optical systems, you can draw an arbitrary curve and order a filter to match this curve. And it's actually just as easy as in electrical. Yeah. Okay. So just to summarize, okay. So just kind of to summarize all the things we said in the last couple of lectures, I'll describe a practical system. If I had to build a practical system where, let's say, I had a sensitive sensor, let's say I had a CCD camera, which is like a webcam, and I needed to connect it to a computer. Okay, and based on what I see, I needed to control some big motors. And the whole thing was a servo system. Like the big motors were the actuator, they moved something, and the camera looked at it and fed back the signal. And this is 10 meters away, and say it's a big motor, and this is, say, 50 meters away, and I have to think about the practical things, how to interconnect such a system. So actually it's not so simple because most of these cameras today have a standardized interface like a USB, so I don't really have the freedom so much to design the system because I have to buy a camera with some existing standard. But let's say that I'm not using a standard USB camera, I'm using a camera of the old-fashioned, like a video camera, because a USB camera, let's say, is not fast enough for me. So I have a high-speed camera, and these high-speed cameras just have video coming out. Okay, so let's say these are the dimensions. So what would I do about shielding? What will I do about grounding? What will I do about filtering? Okay. So the computer is plugged into the power lines. I have no choice. The computer is grounded. So this part I have no choice. Okay? Now the motor, usually for safety, is grounded because the motor is part of a machine, and the machine has to be grounded by code for safety. Any metal structure with electrical in it has to be grounded. So I really don't have a choice here. This has to be grounded. It's too much trouble to isolate the motor electrically, especially if you're not sure you need it. Now the camera, I have some choice here. I can ground it or not ground it because the camera has a power supply. Power supply, this is a small power supply. I don't have to ground it. So, okay, so the first question is, interconnect. What would I use to interconnect the camera to the computer over 50 meters? And again, I have a choice as just a straight wire, a twisted pair, a shielded wire, a coax. I have all the choices we discussed. So what would you use? Shielded, some other ideas? So if you want to be scientific about it, you say, what is the frequency I'm talking about, and how does this compare to the wavelengths? Like, you can make a good guess, but the scientific way is saying, let's say it's a 10 megahertz high-speed camera, it's a 10 megahertz bandwidth output, which is about the right number for a video camera or high-speed camera. So what would I use to interconnect? Who thinks coax? Okay, who thinks shielded? Who thinks twisted pair? So the rest have no opinion. Okay, so 10 megahertz lambda is 30 meters, right? Because 1 megahertz is 300 meters. It's easy to remember. Now this is 50 meters, so that's actually more than lambda. So certainly I have to think of transmission lines here. It's not just a wire. Because the camera output can be all kinds of signals, all kinds of frequencies, depending what the camera is looking at. The camera can look at a straight wall and then the output is almost DC. Camera can look at a busy scene and the output is full of pulses. So basically I need something which is frequency independent. I can't just use a wire here. It has to be a controlled impedance connection. Okay, so I have no choice here. If 50 meter, I have no choice. If it was 5 meter, maybe shielded wire would be good enough. But even 5 meter, it wouldn't work. If this is a regular high-speed camera, 10 megahertz, even if it was 1 meter, it has to be coax. Otherwise, it wouldn't work. Because the spectrum of the camera is kind of spreads all over. It could be, depending on what the camera is looking at, the spectrum can be any shape. Okay, up to 10 megahertz, and you want to represent the spectrum faithfully, because if you shift the spectrum by this being not flat, then you shift what the image looks like. So this has to be a coax, okay, and because of that has to be grounded at both ends. There is no choice. A shielded wire, you can ground at one end or ground at both ends. Coax doesn't work if you don't ground at both ends, because that's part of the whole idea of what a coax is. So I basically have no choice. I have to ground the camera, because if I have a coax, both ends have to be grounded, and this typically would be a 75 ohm coax, simply because for some strange reason video equipment doesn't work on 50 ohm, works on 75 ohm. So that's some old convention, but so if you buy a camera and a coax comes out of it, it will be 75 ohm. But if the camera is not a coax and you decide to attach a coax to it, then you could pick 50 ohm as well. But if the camera already has a coax connector, it will always be 75 ohm. Or almost always. Okay. Okay, so this has to be coax. Okay. Now what would I use to connect the computer to the motor? Obviously the computer is driving here. There's some power amp. There's an amplifier. Just please add the amplifier to your sketch. So if you have an amplifier, and this is 10 meter. Okay, this total is 10 meter, as before. So first I have a question. Should I put the amplifier near the computer, or should I put the amplifier near the motor? Now this usually doesn't have a simple answer. It depends on convenience. Because if this is a high power motor and you put the amplifier near the computer, all these lines have to be very heavy lines to carry high current. So here, let's say for practical reasons, because this is in an inaccessible place, I have to put the amplifier near the computer. Okay? Basically I have a control cabinet, it has a computer and amplifier. I don't want any electronics here because this is some machine tool far away, and that's 10 meter. Okay, so what will I use to connect the amplifier to the motor? Again, coax, shielded.
There's a question going back. What
Yeah.
happens if the coaxial get left to be grounded?
Pardon?
Why do both ends of the coax cable?
Because coaxial cables is working at frequencies where this is a significant part of the wavelengths, and you want to force the voltage to be zero at both ends. Okay, ideally a coaxial cable should be grounded everywhere, not just at both ends, but it's not practical because you don't want to end up with standing waves. Okay, but practically you have to ground both. Basically all the boxes which are connected with coaxial cables, the boxes themselves are grounded. Right? So you don't have much choice, because if you make a box with a B and C, the box itself is metal, it's grounded, so it grounds the cable at both ends. But even if you had a choice, here you have a choice because the camera is a little floating box and you have a separate power supply, so you actually have a choice whether to ground or not the camera. But if you want this to behave as a coaxial cable, you have to force 0 volts at both ends, so you have to ground it. If it's a shielded wool cable, you wouldn't have to ground the other end, say, to avoid ground loops. Okay, so how do I connect these 10 meters, assuming these are high currents, because I want to put the amplifier near the computer? So let's say it's a 3-phase motor. I'll explain in the next section what a 3-phase motor is. I know we didn't talk about actuators yet, but you know roughly what a 3-phase motor is. So, pardon? Yeah, not a pair, but 3. Right? Because it's not a 3-phase motor, needs 3 wires. Triplet, yeah. So I would put in a twisted triplet, and because I don't want to radiate noise. So, okay, so this will be twisted, but should I put in a shielded twisted triplet or just a twisted triplet? So basically what I'll put in is what's called an electrical cable. It's already twisted inside, like when you buy an electrical cable, a high power cable, it's already twisted inside and everything, but I would also want it shielded, because this will be most likely a switch mode amplifier. Even if it doesn't say on the outside, if you buy today a power amp, as I said before, inside this will be switch mode, or what's called PWM, pulse width modulation. So this will radiate like crazy. In spite of the twisting and everything, this will be running tens of amps at very high rise times. Like I mentioned before, if you put a scope on this, you don't see sine waves. If you put a scope on this, you see just millions of pulses at very high rise times. So this is a very bad source of radiation, of interference, even if you twist it. Okay? So you would still have to shield it, but this is not a coax, so you can ground the shield at one end, at both ends, it doesn't matter. Okay, typically you will ground it at both ends. Typically you will connect the shield to the amplifier, and the amplifier will be grounded, and you'll connect the shield to the motor, and the whole thing will be grounded by code, because this is a metal structure. Okay, but it's not grounded at both ends to be like a coax. It's just grounded both ends because how usually the codes work. You have a conduit, it's grounded, you have to ground both ends. But the important thing here is that it's shielded, not that it's a coaxial cable. Yes?
Would it be an advantage using a coax cable then?
You couldn't buy a coax cable which has 3 wires inside. Right? It's just not standard. And also you couldn't buy a coax cable with heavy... You could, it's very expensive. So you could use 3 coaxes. What you could do is use, instead of 3 phases, you can use 3 coaxes, and that actually wouldn't be the best, because then it's not twisted together. So at the end you don't do that. Okay? So you use a regular electrical cable, which is a twisted triplet, but with a shield. It's very important to remember the shield. Okay? Because it's switch mode. Yes?
Is there, other than for power cord, is there commonly used unshielded twisted pairs?
Yes, because inside equipment, when you open equipment, the internal wiring a lot of times is twisted pairs. But to go big distances, it's usually shielded, because today everything is switch mode, that's why. In the old days, it was more common to just have long twisted pairs, because things were linear. Okay, so this is good. Now what about filtering? So So we discussed interconnect, we discussed grounding. Where would I put some filters? Okay, so we already know there is a filter, and we already know you always put it at this end, not at this end, because at this end it also stops all the noise picked up on the cable. So I put in a filter here. Okay, and now if the camera has 10 megahertz bandwidth, like the image has 10 megahertz information bandwidth, what kind of filter do I want here? Remember, that's an analog camera. Just for the example, I picked an analog camera, not a USB camera. So that's actually a signal here. If I look with the scope, I actually see a signal, a video signal like this, which is analog, but carries 10 megahertz of information. So what do I want here? Do I want 10 megahertz, 20, 30, what do I want? So, 30, yeah, minimum that I want is 30 megahertz, because I don't want to be marginal, I don't want to add phase shifts. Okay, although the information contents here is actually low, because the camera refreshes only 30 hertz. So the information content is low, but the output video is 10 megahertz. I have no choice. Although my information is only 30 hertz, I still have to run the full 10 megahertz, put a 10 megahertz filter. So that's kind of makes it difficult, because I need a very wide bandwidth until the card here, which samples and digitizes the camera output. Now another way would be to put a module here, which digitizes the camera right here, and then I come out with an 8-bit or 16-bit bus, and then the data rate is much lower on each line. And that sometimes you have to happen. Sometimes you look at it and say, this is going to be a very long cable, very high frequency. Maybe it's better to already convert it here to digital, and that's what a USB is, right? Okay, but USB is still serial, but you can convert it to parallel digital. And then you have many parallel lines, and the data rate, if you have 8 bits, is on each line 8 times less. So that's kind of system design considerations. I wouldn't get into that. But in general, you have to have a filter. And in this case, the filter has to be very wide bandwidth, even if the information is changing slowly, because the camera outputs it in a format which needs a high bandwidth. And you probably want a filter here, because if you're going to transmit over 10 meters, many amps pulsing, even if you have twisted and shielded, if this equipment sits near other equipment, it's not a good idea. It's better to filter it a bit more here. Although most amps, as I said, already come with a filter. Like the typical amps you've seen is servo amps, like servo amps for motors or variable frequency drives that change the frequency. All these have some kind of filtering inside, but they still pulse. But the pulses are a bit rounded, so instead of pulsing like this, these amplifiers have filters which limit the rise time. Because the steeper the rise time, the wider the spectrum it radiates. So if you just limit the rise time, it already makes a big difference. So what they do in all these modern amps, they can't filter it enough to get the DC values. They don't need a massive filter, a high current, high power filter. They rely on the inductance of the actuator to provide the filtering. They basically rely on the fact that mechanically it cannot respond fast enough, and the inertia maybe. Inductance and inertia give you the filtering, but they can filter it a bit to round the pulses a little bit. And that makes a big difference, because in theory, if the rise time is 0, in theory, if the rise time of the pulse is 0, the spectrum it radiates is infinite. Because that's the Fourier transform, right? To get 0 rise time, you need an infinite spectrum. So because of that, even limited the rise time a bit with a filter like I mentioned they all use this kind of filter. So even putting this in the power amp and limiting the rise time, let's say to a microsecond or 2, makes a huge difference to how much it radiates. And it's required by code. Like if you build something, anything today, it has to pass FCC. FCC is the same Federal Communications Committee. And in Canada, it's part of DOT, I think. I forget what the Canadian equivalent is. So anything you sell which has electronics inside, especially power electronics, has to pass this regulatory committee which measures how much noise it radiates. Right? And there is a little icon saying FCC. Same as Standards Institute, same as UL or Canadian CSA. There's also an FCC registration. So they check it. They check if you put some filtering inside so it doesn't radiate like crazy. Is that clear? Good. So I'll see you on the 25th after your break. The assignment is due first thing on the 25th.